All right, well, hey everybody. This lecture is kind of a series of videos, and so I'm going to kind of pop in and pop out. And there's links to the videos, so you can watch them on your own, or you can view the videos in the PDF if you're on a regular computer. Unfortunately, viewing the videos in the PDF does not work so well on the iPad. But it's just kind of a bunch of sort of interesting things that I've sort of mushed together in this lecture on polarization, interference, and refraction. So we're going to be talking about properties of light and electromagnetic waves. The first thing is this interactive, which is from the University of Colorado, which is why it looks like it's from South Park. So let me go ahead and share the visuals from that demo. So here we go. So we've got an electron that's here, and there's some electric field that the electron is producing, right? So the electric field is pointing towards the electron, and in principle, if you had an electric field probe, you'd measure what it is. But the point is that if you wiggle the electron here, that produces changes in that electric field that propagate according to the speed of light. And so if I take this electron and I click on it, and I wiggle it around, there's some signal that's going to propagate at the speed of light until it reaches over here at this kind of house that has another electron inside of an antenna that's trying to measure this thing. So again, the electric field is pointing towards the electron, but we can kind of track the changes in that electric field, which is what this straight line is. And so what I can do is I can try to wiggle this electron until I can get this electron and this antenna to wiggle. And so I can try to do that. Let's see how well that works. It's probably not going to work that well, but I can try to do it. I'll try to wiggle it back and forth. It's sort of roughly the same thing. And you can see that this electron on the right is kind of moving just a little bit. I'm not very good at doing it by hand, but if I configure this thing to oscillate at some speed, by the way, electrons are negative, so the electric field points the opposite direction of the force. But anyway, so if you oscillate this thing very carefully in a sine wave, you can get this thing to oscillate as well. And this is basically how radio waves work, right? There's some radio station that has a gigantic piece of metal in which it's oscillating the electrons back and forth inside of that metal. And then your car has an antenna, and the electrons in the antenna in that car, which antenna is just a fancy word for a piece of metal, those electrons respond to those changes in electric fields. And then that ultimately is how you get the signal. So that's one of the things I wanted to talk about today in this lecture. Unfortunately, this is a Java interactive, and so it's probably not going to work on most of your computers, but it works on mine. You can see how it works there. So that's kind of how electromagnetic waves propagate. The next thing is on what's called the polarization of light. And so there's going to be a video, and I'm going to mute my microphone so the sound isn't terrible. And then I'll go ahead and play the video. You can also click on the link. Click on the link here. Let's see if I can do that. You can also just click on the link here just to see it. But let me go ahead and mute my microphone so there's not interference.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.
So that was a basic introduction to polarizers. So if you've had polarized sunglasses, there's all kinds of different polarizations of light, and the polarized sunglasses only let through one kind of polarization. The next video is from Walter Lewin at MIT, and he has a very nice demo that we're going to watch. If you click this link, you'd have to skip forward about 40 minutes, but he's going to explain his understanding of polarization with kind of an interesting experiment that I actually don't quite have the ability to do at Marion. So let's watch Walter Lewin there. If you want to click the link, that's fine. If you want to watch it in the video, that's fine too.
How the radiation, how the electric field is oriented relative to a charge that we are accelerating. In the middle here, we accelerate a charge up and down. Frequency omega. Whatever radiation you want to make, fine with me. You can make omega as large as you want to. For one thing, notice these waves here, these snakes, represent electromagnetic radiation. And nothing is going out in this direction, and we understand why. The maximum is going out in a plane perpendicular to this direction. That is this, and this. And notice that the E vector that you receive when you are here is perpendicular to R. This is R, and it is perpendicular. And notice what I said, that A and R and E are in one plane. A, which is the acceleration, R and E are in one plane. A, R, and E are in one plane. A, R, and E are in one plane. So you can always determine the direction of the oscillating electric field. And if you go at an angle theta, which is neither 0, which it is here, nor 90 degrees, which it is here, here, and here, but if you have something in between, then notice that the E vector here is drawn a little smaller. That is that sine theta here. And consequently, the pointing vector in that direction will be smaller than in this direction. And in this direction, the pointing vector will be 0. We call this radiation, whether you're here or there or there or there, we call that linearly polarized radiation for the simple reason that the electric field is oscillating in one direction. It's linear. And I'm going to produce for you linearly polarized radiation, and I have two demonstrations for that. So I'll get the lights back on again. So let's discuss these demonstrations. I have here a transmitter which transmits at 10 gigahertz. That is a wavelength of 3 centimeters. You wouldn't call that radio, you would call that radar, but that's just a matter of names. And we have also a receiver. We have a transmitter and we have a receiver. The transmitter is here, and the receiver is here. If I give you a three-dimensional picture, this is my coordinate system. This is coming straight out of the blackboard to you. That's what I meant by this. Then the transmitter is aimed like so, just like this. Current is going to be oscillating like this. And the receiver, think of this as my radio, which is receiving, is here. And the antenna of the radio is also in this direction. And so, the electric field, which you see here, which comes from these oscillating charges, which oscillate, by the way, at a horrendous frequency, 10 billion times per second, their electric field is perpendicular to R, this is R, and the electric fields, R and A, are in one plane. So that means that the electric field that arrives here is oscillating like so. And therefore this antenna, this receiver, is very happy. The radiation comes in exactly in the right way, and so it will receive it. We have modulated this signal with an audio signal, amplitude modulation, as we discussed that earlier, that you also use with radios. And we modulated with approximately 1 kilohertz audio signal. And we'll make you listen to that audio signal. And you can tell then that this receiver is indeed receiving the 3 centimeter radar from this transmitter. That's what we will first do. So I'll just turn on the transmitter, and here you hear 1 kilohertz. This is the modulated signal, and it's received by this antenna, which is a straight wire like this, and this is the emitter. And to demonstrate to you that it really goes from here to here, I put my hands in between. My hands absorb 3 centimeters. It's not there anymore. There it is. It's not there anymore. But now I'm going to rotate this antenna by 90 degrees. So this one is going to be put in this position. So now the electric field, so I'm going to put it now in this position. So the electric field now is going up and down like so. But the receiver doesn't like that, because the antenna of the receiver is like this. So it cannot drive any current. And so you won't hear anything anymore. So what it means is that I have changed the direction of polarization by 90 degrees, and the receiver cannot see that. I'm going to rotate it now 90 degrees. And it stops. So now the electric field goes like this. The wire here, the antenna, is like this, and the wire says, sorry, I can't hear you. But all I have to do now is rotate the receiver 90 degrees, and so I can rotate this antenna and put it vertical, and then, of course, it's happy again. So if I rotate this 90 degrees, there comes the signal back. So now the E field is like so, and the antenna receives it like so. Now I have one brain teaser for you. And I want you to think about that. We can actually have a vote on that. I have here a wooden frame with metal bars. No trick. Metal bars. And I'm going to put that in between here. So we have the situation that we are transmitting electromagnetic waves with the E field going like this, and the receiver is perfectly happy. The receiver is also aligned like this. There you have it. I can put this grid in like so that the bars are in the same direction as E, but I can also put it in like so that the bars are perpendicular to E. If I make you a drawing, if you would look in this direction, then I can do one of two things. Either the bars are like so, or the bars are like so, but in both cases is the electric field coming in like this. Who thinks that if I have the bars vertical, that the electromagnetic radiation will go straight through without any problem? Who thinks that maybe it will not get through? Who thinks it will get through? Who thinks it will not get through? Now I do this. Who thinks that the electromagnetic radiation, the oscillating E field, can easily go through this? Who thinks it will not get through? It's very evenly divided. We have about 25, 25, 25, 25. Okay, we'll see. 1 kilohertz. E field is like this. Receiver is receiving it. What do you want me to do first? This or this? Let's do this first. Nothing. It's not absorbed. Go straight through here. Now rotate it 90 degrees. I kill it. So in this configuration, the electromagnetic radiation does not get through. I want you to think about it, and if you have some sleepless nights about it, that's okay too, that's very healthy. I have a second demonstration, and that has also to do with the polarization of electromagnetic radiation. I have here 75 megahertz transmitter. So that's more like radio stuff. That is a 4-meter wavelength. And this is the antenna. This is the transmitter. So let me give you the numbers. So this is 75 megahertz. And that is 4 meters wavelength. And I'm going to turn it on like now. You don't hear anything. It's not connected to any receiver yet. Oscillating. Making electromagnetic waves going like this, going up. Not much is going in this direction. I have a very special receiver. A very special one. And that very special receiver is this. It's just a straight copper wire cut in the middle, and the left side and the right side are connected with a light bulb. So if there's a strong current going through here, that means if it receives a strong signal, then the light bulb will indicate that. And I'm going to make it dark so that we can perhaps see that light bulb. So that is transmitting. And I want to show you several things. The first thing I want to show you is that indeed, if I hold this parallel to the transmitter, that I can receive it. The electric field is now going like this, and so this receiving antenna is very happy. But now look what happens. It's the same thing I did with the radar receiver. I rotated 90 degrees. And now the E field that comes in this cannot cause any current like this. So the light bulb goes out. I can also show you, which is obvious, that if you go farther away from the transmitter, that the strength of the signal is less. Remember, the pointing vector goes as 1 over r squared. So the light in the light bulb should go down by 1 over r squared. So I go a little closer, cannot too close, because I can really burn out the bulb if I come too close. But you see it's quite bright now, and when I walk away, by holding it still in the right direction, you see that indeed the light bulb gets fainter. 1 over r squared relationship. What is also interesting, we can explore how much radiation is sent out by this transmitter in the direction of the antenna, which is the direction in which we argued that no radiation should go out. So let me walk over here, or let me walk to the other side, because it's darker here. So right here, I am now standing such that theta is 0. No matter what I do, whether I hold my antenna like this, or like this, or like this, there's nothing I can do. I can even come a little closer, you see no light. Because there is no energy flowing in this direction. No electromagnetic wave. Largely going out in the plane perpendicular to the antenna. But of course, if I'm here, which is not exactly perpendicular, then of course I do pick up also some radiation. Okay, see you Friday.
So I hope you enjoyed that video. I think it's some pretty interesting experiments that he was doing there, and just to talk about the microwave experiment, you know, when he puts that grid between the two microwaves, and we have this equipment at Marion, and you guys actually have a microwave lab, and if you want to know more about what's involved in that microwave lab, there is some videos that we received from Columbus campus on sort of what's that about. But you know, one of the things in that microwave lab is you put down that metal grid of parallel pieces of metal, and basically if the electric field is oscillating like this, you know, up and then down and then up and then down. We talked about plane waves in the last lecture. If the electric field is oscillating like that, and then you put some sort of grating, some metal grating that's like this actually will stop the electromagnetic wave, because these pieces of metal are conductive, and the electric field inside of a conductor is 0. And so if you put an electric field like this or electric field like this, the electrons inside of this metal can move to neutralize that electric field. And so if the electric field is 0 inside of this thing, then it's not going to be 0 on the other side. Whereas if you have an electric field that's doing this, and you give it pieces of metal that are this way, the electrons can't move up and down so much. And so it's very limited in the way that it can attenuate the beam. It can attenuate the beam just a little tiny bit, but not nearly as much as if that piece of metal was sort of encountering it this way. So that's so he challenged the class to think about why is it that it happens that way, and that's the explanation, is that if the electric field is in the same direction as the metal, the electrons can move to neutralize it. Electrons move very, very fast, and so that's part of why it's as effective as it is. And the other thing that he did is kind of walking around the antenna and sort of seeing, like, all right, well, if I have my antenna here, I can get a signal here, but not if I do this, and not if I do that, and if I walk over here, I don't get a signal. This to me reminds me a lot of wireless routers. So in my wireless router, actually I'm going to pause right here. Let me get my wireless router and I'll show you what it looks like. The thing about this wireless router is that, we've got these antennae here. And there's a lot of wireless routers that don't have antennae on them, which is fine. And what that really means is there's antennae inside of it. But you have these antennae here. And when you have an antenna, as Walter Lewin was talking about, the change in electric field goes out sort of this way, this way, right? But if you're up here, you don't get so much of a signal. And the reason is that as the electrons go up and down on this antenna, because of the signal, well, then if you're over here, you can measure that change in the signal rather well, because the direction of the electric field is changing. Whereas if you're up here, well, the electron might be moving closer to or further away, but that's like a 1 over r squared thing, and that doesn't make a very big difference in what the electric field is up here, it turns out. And so when you have a wireless router like this, my advice for what you want to do with it is that in order to receive the signal in different parts of the house, you don't all want it to go the same. You don't want to have all these antennae going the same direction, because that means that only the devices that are sort of in this plane can receive the signal from the Wi-Fi router. So my advice is you probably want one of these things to be bent, and you probably want one of them to be off at sort of an angle, so that this one is broadcasting to the devices that are sort of in this plane, whereas this one is broadcasting devices that are in this plane. And so say for example, like right now I'm up in the 2nd floor of my house, and so this one is doing a good job of broadcasting to all the devices that are on the 2nd floor. But this one might be doing a pretty good job of broadcasting more to the things that are on the 1st floor of the house. And so you don't all want these things going the same way. And we used to have a 3rd one on here that snapped off, probably because one of our pets stepped on it or something. But it's best to have them going in sort of all different directions to try to make sure that all the devices get a good signal. This physics is the same as the physics that Walter Lewin was using. He was doing it at 75 megahertz. This is operating at 2.4 gigahertz or 5 gigahertz, but the physics is the same. Now the next lecture Walter Lewin is going to do is not on radio waves. It's about optical stuff, and so I'm going to let him do what he does best, and I'll mute my microphone so you can hear the sound just a little bit better, and then we'll talk about it afterwards.
I'm going to talk about light. Light is an electromagnetic phenomenon, and already in the 16th century, way before Maxwell, a lot of studies were done of the interaction of light with water and with glass. And the kind of experiments that were done as follows. Say this is air. I call that medium 1. And this is water. Call that medium 2. And I have a light beam that strikes this surface. Light comes in like so. And I define this angle as the angle of incidence, and I call that theta 1. This is the normal to the surface, and we call that the angle of incidence. I will see now that some of that light is reflected with an L as in lion, and some of that light goes into the water, and we call that refracted with an R as in Richard, and this angle we'll call theta 2. And it was a Dutchman, Willebord Snellius, who in the 17th century found 3 rules that govern the relation between these 3 light beams. The first one is that this beam, and this beam are in one plane. As you see, that is my plane of the blackboard. The second thing that he found, that this angle, theta 3, which is called the angle of reflection, is the same as the angle of incidence. That was known before him, of course. And then the third one, which is the most surprising one, which is called after him, which is called Snell's law, although his name was Snellius, is that the sine of theta 1 divided by the sine of theta 2, if we go from air to water, then that ratio is about 1.3. If you go from air to glass, it's a little higher. It's like 1.5 or so. He introduced the idea of index of refraction, which I will call N, as in Nancy, index of refraction. For vacuum, the index of refraction per definition is 1, but it's very closely the same in air. We always treat it as 1 in air. And in water, the index of refraction is approximately 1.3, and in glass, depending upon what kind of glass you have, it's about 1.5. And so we can now amend this law, Snell's law, by writing here N2 divided by N1, N1 being the index of refraction of the medium where you are, your incident beam, that's why I put a 1 here, and 2 being the index of refraction of the medium where you're traveling to. You refracted into this medium. And so you see indeed that since water is 1.3 and air is 1, that this ratio for air to water is 1.3. And this is called Snell's law. And it is immediately obvious that if you go from air to water, or you go from air to glass, that angle theta 2 is always smaller than the angle theta 1, because this number is larger than 1. But if you go from water to air, then the situation is reversed. And that's what I want to address now. That's actually quite interesting. So now, my medium 1 is now water, and my medium 2 is now air. And so now, I go from here to here, and so here I have my angle of incidence, theta 1, and here I have my angle of reflection, that is this theta 3, and now here I have my angle theta 2. And so if I write down now Snell's law, then I get the sine of theta 1 divided by the sine of theta 2 is now N2 divided by N1, but N2 is 1 divided by 1.3 if we go from water to air. And what is so special here is that theta 2 can obviously never be larger than 90 degrees. And so if you substitute in here theta 2 is 90 degrees, then you will find that theta 1 then is about 50 degrees. And if you apply this equation and you substitute for theta 1 an angle larger than 50 degrees, you're going to find the sine of theta 2 being larger than 1, which is nonsense. It cannot happen. And so nature ignores Snell's law, and nature says, sorry, I can't do it. And what nature now does, if the angle of theta 1 is too large, in this case with water larger than 50 degrees, this is not there anymore, and all the light is now being reflected off that surface. And we call that total reflection. Total reflection. So total reflection happens when theta 1 is larger than a certain critical angle, and the sine of that critical angle, for which I write CR, is N2 divided by N1, but there is a condition, and the condition is that N1 must be larger than N2. If that's not the case, then there is not total reflection. And total reflection is actually very interesting. It has practical applications, which I will discuss with you shortly. But I first want to do a demonstration in which I want to show this to you. I have here water, and here is air. And I have a laser beam which I can shine in, and I can change this angle theta 1 and slowly increase it. And you will see that when I approach the 50 degrees, first of all, you will see that theta 2 increases, 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 and then when I approach the critical angle and exceed it, then we have 100% reflection. And this has practical applications. And we're going to show you some of these practical applications too. The most important practical application is fiber optics. If I have a fiber and it is properly designed, so this is a fiber, and some light comes in here, and it hits here, so this is, say, some plastic or glass, and this is air. If this angle of incidence is larger than the critical angle, 100% reflected. And so nothing comes out in the air, 100% reflected. Here, again, the critical angle is exceeded, and so 100% is reflected, and you can go through this whole thing for miles on end. You can put even knots in there. As long as you never exceed the critical angle, that light will propagate, and there will never be any loss of light. And that's why people are very much interested in it. You can transport even images, as I will show you, through fiber optics. I have here a fiber optics which has 4,000 fibers in it, 50 microns in diameter each. And we have a laser beam here. And the laser light will come out. I will show you the laser light shortly there. And it doesn't matter what I do with the fibers. I can even go 180 degrees and shine them there. As long as inside the fiber, I always exceed the critical angle. Oh, I don't want the television anymore, so we can turn this off. And let's here have the laser light. There it is. Here you see the laser light. Okay, now look at this bundle that I have here. I'm turning it into an absurd snake, almost like an S. All the light still comes out. So it goes all the way through. I'm going to turn it 180 degrees around, turn it to the wall there. There it is. So there's an amazing phenomenon that this light doesn't get out in the air. It stays inside the fiber. And that's the idea behind fiber optics. I have another application of fiber optics right here, which is very similar. you can send an image through fiber optics. This is my fiber optics now, thousands of small fibers. And I send a message in here, this side, an image. Could be a person, could be a text. And here we have a TV camera. And we can watch that image. On this side of the fiber appears that image. And this television camera will be able to see that image. And let's see whether we can show you that message. Okay, I have to do something here again. I think you're going to, there it is. So you actually can see the individual fibers. You see them? How interesting? Each one, these are individual fibers. And their diameter is probably not much more than 50 or 100 microns. Let's see what message there is for you. Oh man, exam 3. You don't want to hear about that, do you? Well, that depends on what the message says. Problem? No. No. Problem 1. Problem 1. The figure, below. Oh, I must have, that's the wrong message. I couldn't possibly meant to give you away the exam, of course. So I apologize for that I showed you the wrong message. But at least it demonstrated to you that you can send an image through fiber optics, even secret messages. Newton had an interesting explanation for Snell's law. Newton was the man of planets. He was the man of particles, masses, accelerations, F equals ma. And so his explanation came with particles. He says light are particles. So if this is the surface between, let's say, air and water, Newton argued as follows. If light comes in, it has a certain speed, v1. And therefore it has a horizontal component. And it has a certain vertical component. And he says if this light ends up in water, at the moment that it reaches the surface, it gets an acceleration perpendicular to the surface. Why? He didn't tell us. But he said it gets an acceleration perpendicular to the surface. In other words, this horizontal component does not change. That remains what it was. But this component changes. This becomes substantially larger, depending upon the index of refraction, of course. And so the new velocity is now in this direction. And so you see that indeed the angle theta 1 is larger than the angle theta 2. But Snell's law immediately follows from this. The sine of theta 1, this angle is theta 1. So this angle is theta 1. So that's this velocity divided by this vector. And the sine of theta 2 is this velocity divided by this vector. But these two velocities are the same. And so you immediately find that this ratio is v2 divided by v1. A great victory for Mr. Newton. Except there was one problem, maybe, that it means that v2 is larger than v1. And so Newton argued that the speed of light in water is larger than the speed of light in air. And in glass, of course, it would be even larger. Now there was a Dutchman, and the name of Dutchman was Christian Huygens. Huygens. And this gentleman suggested that perhaps light are not particles, that they are waves. And this guy came up with a genius idea, which we now know as Huygens principle. At least you call it Huygens principle. But we don't call it Huygens principle. You see, this sound, uy, is pronounced in Dutch as ui. None of you can say ui unless you're Dutch. To make it worse, this sound you don't have either in English. That's a ch. None of you can say a ch unless you're Dutch. let alone that you can say the combination Huygens. Anyone who comes forward to me after this lecture and who knows how to pronounce the word Huygens has to be Dutch. I will be kind to you and call it today Huygens principle. So Huygens came with the following idea. Here is a source of electromagnetic waves. And these electromagnetic waves propagate out in a spherical way. Not unreasonable. And so you even see here the wave crests. And so he defined the surface at the leading part of the wave, where all points are in phase. He called that the wave front. So this is the wave front. And he now postulated that each point of the wave front individually oscillates at the same frequency as the source and produces spherical waves. We call them secondary waves, often also called wavelets. And that the envelope of the wave front of these secondary waves is now the new wave front. So it works as follows. Each point that you can choose as many as you want to, starts to oscillate at the same frequency as the source and produces on its own spherical waves. There they go. And the new wave front is then here. And this is called Huygens principle. Because he doesn't give any explanation of why these points do that. He hypothesized that. And this principle can explain Snell's law in a very easy way. I want you to read up on that in your book. And you will see that it is very easy to explain Snell's law with this principle. Except that now you will conclude that the sine of theta 1 divided by the sine of theta 2 is V1 divided by V2. And therefore, Huygens predicted that the speed of light in water is lower than the speed of light in air, whereas Newton predicted that the speed of light in water would be higher than the speed of light in air. So the question now was, who was right? Are light particles or are they waves? Well, the wave-particle idea of light has been a very long-standing issue in physics. And I will show you, I think next week, or maybe after the exam, how Young in 1801 conclusively demonstrated that light are waves. So it looked like Huygens was going to be the winner. On the other hand, I showed you last lecture that light can behave like particles, photons, bullets, tomatoes, radiation pressure. That's particles. Mass, the whole thing, the whole ball of wax. And so maybe Newton was right, maybe they are particles. Well, they're both right. There are times that you can actually interpret what you see best by assuming they're waves, and that there are times that it's much better to assume that they are particles with mass, like in the case of the radiation pressure. But of course, the key question now is, who was right in terms of the speed of light? Is the light going faster in water than Newton was right, or is the light going slower in water than Huygens was right? Needless to say that the Dutchman was right. The speed of light in water is lower than the speed of light in air. When we derived the speed of light in vacuum, we used Maxwell's equations. And they allowed us to conclude that the speed of light, much to everyone's surprise, depends on epsilon 0 and mu 0 in a very simple way. I will call it for now V. That was 1 over the square root of epsilon 0 mu 0, and we call that C. If you had used Maxwell's equations as they are valid in materials, in dielectrics, and also in materials that have magnetic properties, then it would be exactly the same derivation, but you would have seen a kappa here, the dielectric constant, and you would have seen here the magnetic permeability. Kappa, if you're not in air, but in glass and water, it's always larger than 1. So you see in front of you that the speed of light in water is lower than the speed of light in air. This can also be written as c divided by the square root of kappa divided by kappa m. And we would nowadays simply write that as c divided by n.
Okay, so I'm going to cut him off there and go ahead and talk about the next thing. But he covered a lot of ground there, including some ground in terms of why is Snell's law the way that it is. So I'm not going to attempt to tread that ground, but Snell's law is a very important thing for this course. There's going to be a question on the exam for sure that's on Snell's law, so let's talk about what that involves. So this is Snell's law, just the equation of it, and the idea is that there's some ray of light that's moving from some medium which has some index n1 that has some angle of incidence theta 1 that moves into some other medium. And just schematically, this is kind of what happens, is that if you're going from air into something that's not air, right? So let's say there's air up here, and maybe this is glass, maybe it's water. The important thing is that this index is more than this index. So the index refraction of air is 1. The index refraction of glass and water and whatever else is greater than 1. And so when that's the situation, according to this equation, if you solve for theta 2, and by the way, this angle is relative to the vertical here, it's not relative to the horizontal, and then I might try to trick you on an exam and give you the angle relative to the horizontal, and you have to figure out what it is relative to the vertical. But if this is the angle relative to the vertical, you can solve for what the angle of the transmitted ray, and that angle changes, again, according to this equation. And you can calculate what that change of angle is. And what you find is that if you're going from a low index medium to a high index medium, such as from air to water, then this angle will get smaller. So instead of, let's see, so instead of going through like this, right, without being bent at all, it's going to go through like that. And so that angle is going to get smaller because of this equation. And so the lesson learned is that when you're going from a low index to a high index, that angle is bent towards the horizontal. What's interesting is that if you're thinking about light that's originating from the high index, so instead of coming in from over here, right, now we're coming in from the high index, so this is the glass or the water, and we're coming out of it. We're going from a high index to a low index. Instead of continuing in that same direction, like this, instead we're bent away from the horizontal. So again, when light goes from low index to high index, the bending is towards the horizontal. Sorry, the bending is towards the perpendicular. Was I saying horizontal? The bending is towards the perpendicular when you're going from lower index to the high index. But when you're going from high index to low index, the bending is away from the perpendicular. Again, this is just what this equation says if you solve for it. So earlier I showed you guys, this animation, and they had this sort of dashed line here, which showed that it sort of bends here. It was bending because of Snell's law. Now, what's interesting, and what Walter Lewin was highlighting, is that there are situations, especially if you think about this situation, not so much this one, but this one where the light is originating from the high index. There are situations in which that if the index refraction is large enough and the angle is large enough, then you get a situation in which if n1 is large and if theta 1 is large, then this times this. So for example, if glass is 1.33, and let's say that theta 1 is very large, so that the sine function is close to 1, so this becomes 1.33 times 1, that's 1.33. there's no way that this can add up to 1.33 if, for example, if the index is 1 and the sine function maximizes at 1. So there's situations in which there's simply no way that these two things can be equal to each other. And as Walter Lewin discussed, that's called total refraction or total internal reflection. So just in an experiment, this is kind of what's happening, is that as we're getting a larger and larger angle, eventually this transmitted light disappears. So I can go ahead and start this over again. So this transmitted light, the angle gets closer and closer to horizontal, but then it disappears. And this angle is what we've been solving for with Snell's law, right? But above some angle here, it just disappears. And when it disappears, you see that there's this really nice reflection. And that is the principle that's behind the fiber optics that Walter Lewin was showing off. And he had a demo that was similar to this one, but I think it was just not quite as clear what was going on. So, so that's the point, is that Snell's law is true unless it's not true, unless there's no theta 2 in which that would actually work. And so one of the things we're going to do on the worksheet, one of the things we're going to do on the homeworks, is try to figure out exactly what angle that this happens. And the angle that this tends to happen is, for example, when this incident angle, when this sine function, when this sine function is close to 90 degrees. So when the angle is very close to 90 degrees. And that's ultimately how you find what's called the critical angle, which here they experimentally found the critical angle. The critical angle is right there. So that's why they sort of hover on that for a second. So mathematically, you can use Snell's law to figure out when exactly does that critical angle theta 1 occur. Again, the light is going through some sort of glass, and so that's high index, and so it's going from high index to low index. And because of the shape of this glass, there's no bending of the light kind of at this surface. And so if I was there with you, I have the materials at Marion to sort of do this demo, but because I'm not there, we'll just have to watch the video there. So I hope that's a good introduction to the topic. What I'm going to do now is just briefly show you the worksheet for today. So the worksheet involves going from air to glass to air, which is basically a window, right? Any window involves air on one side, there's glass on this side, and then there's air on the other side. And sort of the first thing you need to do is figure out which one of these things is correct. And what we're going to do through the course of this worksheet is to apply Snell's law at each interface and try to figure out what is the angle at the other end. There is a question on the final that is very similar to this. And so I'm giving this worksheet to try to prepare you for that. So that's the basic idea. And I hope that I've given you some of the tools to work on that. So, all right, go ahead.